Hello everyone, welcome to this amazing channel of Infinity Learn by Sri Chaitanya. It's NEET segment. I'm your host and host and you all call me AB. Guys, today we are going to discuss one of the chapter known as periodic table. And in NCERT it is mentioned as classification of elements and periodicity in properties. Okay, so yeah, we'll not waste much time because today we need to complete this entire session because NEET examinations are close. So what I have planned is to take maximum topics. Okay, although this is a small topic, but yes, it is like you can expect at least one or two questions from this particular topic. If not directly from this topic, this chapter is really very important and this will be related to many other chapters as well, be it organic or be it inorganic. Okay, so guys, time waste नहीं करते हैं, start करते हैं session को. So as I said, your host and host, you all call me AV, and today we are going to discuss periodic table. Okay, so proceeding further, कुछ ground rule sets के जो हम use करने वाले throughout the particular session. If I'm audible, visible, slides are visible, everything is good, technically we are sounding great, so you will be typing yo in the chat box. The moment you type yo in the chat box, इससे मेरे को ये समझेगा कि ठीक है, टेक्निकली हम सही जा रहे हैं एंड कोई प्रॉब्लम नहीं आ रही है. ओके, देन सेकंड, इफ यू हैव अंडरस्टूड द टॉपिक, कोई डिफिकल्टी नहीं है, सारी चीजें मजे में चल रही है, सो विल बी टाइपिंग वी स्टैंड्स फॉर विक्ट्री. ओके, वी स्टैंड्स फॉर विक्ट्री इन द चैट बॉक्स. लास्ट वन विल बी टाइपिंग सीसी, दैट मीन्स व्हाट, क्लैप क्लैप. अगर क्वेश्चंस पूछ रहा हो, कोई पार्टिसिपेट कर रहा है, तो विल डेफिनेटली टाइप सीसी इन द chat box. Okay, clear? So let's get started. The first thing that comes in my mind is what is periodicity. Okay, the first thing that comes in our mind is what is periodicity. ये word का मतलब क्या है? Okay, chemistry के aspects obviously मैंने definition लिख रखा है, उससे कोई problem नहीं होनी चाहिए. But actually what is periodicity? Okay, periodicity, if I'm not mistaken, or if I want to give you an example, can I say it is sunset? It's periodic in nature, right? एक particular time पे sunset होने ही वाला है. Okay, in 24 hours at a particular time sun will set, right? If sunset is periodic, can I say sunrise is also periodic? Right? Even a day in our life is periodic. That means after every 24 hours the day will change. Again, it's periodic. It's a cycle of 24 hours. So can I say that what is periodicity? Something that occurs after a particular period of time. That is known as what, periodicity. And अगर इस चीज को केमिस्ट्री के कॉन्टेक्स्ट पे बोलना हो तो क्या बोलेंगे? It is the repetition. Okay, so it is the repetition of a property of an element after a certain fixed interval of time. Okay, clear? Sure. So yes, ये क्या होता है? Periodic. Okay, something that will repeat after a certain interval of time, that is known as what, periodicity. Right. Second, periodicity की जरूरत क्यों पड़ी? Okay, what is the necessity? क्या जरूरत थी periodicity की? तो ये explain करने के लिए I have taken two examples. One is unorganized library and एक है organized library. Okay, so organized वाले पे बाद में आते हैं, पहले unorganized वाले पे चलते हैं. Suppose there is a, like in your town there is a library which is maintained something like this, and your aim is to find out your 12th standard NCERT chemistry book from this pile of book. How much long it will take? First of all, do you really think that you are going to go this library? या library में जाओगे, book ढूंढोगे और लेके आओगे? Answer is a big no. Possible ही नहीं है. Why it is not possible? Because it is haphazard. It is just dumped in a one place. एक जगह पे बस फेंक दिया गया और इसमें से जाके एक particular book ढूंढना बहुत ज़्यादा difficult हो जाएगा. Right? बट वहीं पे अगर आप स्कूल जाते हो, अपने कॉलेज जाते हो, तो वहाँ पे एक बहुत ऑर्गेनाइज लाइब्रेरी मिलती है. ऑर्गेनाइज लाइब्रेरी का मतलब क्या होता है? देयर आर सेगमेंट फ्रॉम सीनियर केजी टू योर 12th स्टैंडर्ड. राइट, ये सारे सेगमेंट होते हैं. हर एक सेगमेंट के अंदर सब्जेक्ट के भी सेगमेंट होते हैं, लाइक इंग्लिश, हिंदी, ज्योग्राफी, मैथ्स, साइंस, ऐसे सारे. देन साइंस के अंदर भी एक अलग से सेक्शन होगा जिसमें फिजिक्स, केमिस्ट्री, बायोलॉजी आ जाएंगे. केमिस्ट्री में भी एक अलग सेक्शन होगा जिसमें 11th स्टैंडर्ड और 12th स्टैंडर्ड के सेगमेंट होंगे. फिर उसमें 12th स्टैंडर्ड में केमिस्ट्री का बुक ढूंढना बहुत ज़्यादा आसान हो जाएगा. सो राइट, कैन आई से दैट इफ वी आर अरेंजिंग समथिंग प्रॉपरली, ठीक है, तो उसको ढूंढने क्या हो जाता है? बहुत ज़्यादा आसान हो जाता है. ओके, इट रियली बिकम्स वेरी वेरी ईजी टू फाइंड इट आउट. सो दैट्स वाई वी नीड एन ऑर्गेनाइज लाइब्रेरी. In the same way we need an organized way of representing an element. That's why periodic table was invented. अगर ये एग्जाम्पल नहीं समझा तो बेस्ट एग्जाम्पल जो शायद हर लोगों को पता होगा वो है किचन। आगे मम्मी ने किचन बहुत अच्छे से रखा है, राइट, जिसमें स्पून एक जगह पे है, बड़े वाले प्लेट्स एक जगह पे है, कप्स एक जगह पे है, छोटे प्लेट्स एक जगह पे है, बाउल्स एक जगह पे है, राइट। तो ईच एंड एवरीथिंग इज ऑर्गेनाइज। जस्ट इमेजिन व्हाट विल हैपन कि एक दिन मम्मी ने सारी चीज़ों को एक ही जगह पे डंप कर दिया तो क्या होगा? तो ना स्पून मिलेगी ना प्लेट मिलेगा, कुछ नहीं मिलेगा। इसके लिए गाइस क्या होता है, उसको ना क्लासीफाई करना बहुत ज़्यादा इंपॉर्टेंट हो जाता है, उसको प्रॉपरली अरेंज करना बहुत ज़्यादा इंपॉर्टेंट हो जाता है। दैट्स वाई वी नीड व्हाट? पीरियोडिक टेबल। ओके, सो रीज़न वही है, जब चीज़ें बहुत ज़्यादा हो जाएंगी तो उसको क्या करना पड़ेगा, अपने को क्लासीफाई करने की ज़रूरत पड़ जाएगी, अरेंज करने की ज़रूरत पड़ने वाली। सो दैट इज द रीज़न। एंड या in 1800 if you'll see there are only 31 elements known। 31 elements इट्स ओके, ओके, इतना बड़ा अमाउंट भी नहीं है, इतना बड़ा फिगर नहीं है कि हम इसको याद ना रख पाए, इसके प्रॉपर्टीज याद ना रख पाए, तो तब तक कोई जरूरत नहीं पड़ी। बट 1800 से 1865 आते आते, फ्रॉम 1800 टू 1865 द नंबर ऑलमोस्ट बिकम मोर देन डबल, दैट वाज 63। नाउ देयर वाज अ सीरियस नीड of periodicity. Why? Because with this 63 elements, it is really difficult to remember their name, their properties as well. Okay, and knowing the fact that some element shows some element shows same property while other element does not. Okay, clear? And presently we know that there are total 118 elements. Okay, that total what? 118 elements. Clear? And yes, efforts are still going on. Okay, efforts are still going on to invent new एलिमेंट्स एज वेल। ऐसा नहीं कि खत्म हो गया इन्वेंशन, ऑब्वियसली आगे और एफर्ट्स डाला जा रहा है ताकि और नए एलिमेंट्स तैयार किए जाए। क्लियर? नाउ it is very difficult to individually study the chemical properties of every element and the numerous compounds which are found by this element. To ease out this problem, scientists search a systematic way to organize their knowledge by classifying the element. Okay, by classifying the what? Element. Clear? Perfect. आगे बढ़ते हैं. Now, what is periodic table? The arrangement, okay, the arrangement of an element in a tabular form on the basis of their electronic configuration that facilitates the systematic study of elements property. Okay, it is what the arrangement. Okay, let us mark this thing. Okay, it is the arrangement. This is very important. Arrangement of what? Elements. In which form? Tabular form. On the form or like tabular form on the basis of electronic configuration. Okay, on the basis of what? Electronic configuration that facilitates the systematic study of elements. So this is what definition of periodic table. Clear? Sure. Let's proceed further. Now talking about historical development of periodic table. The first one was Joseph Proust. Okay, Joseph Proust simply said that, okay, his name was, if I'm not mistaken, it is Joseph Proust, the first one to attempt to classify the element. What did Joseph Proust say? That all the elements are made up of hydrogen atoms. Okay, all the elements are made up of what? Hydrogen atoms. Like for an example, oxygen. Okay, if I talk about oxygen, oxygen is made up of 8 hydrogen atoms. Okay, just to give you an example, carbon is made up of 6 hydrogen atoms. So 6 hydrogen atom combines to give you carbon, 8 hydrogen atoms combines to give you what? Oxygen. That's how we classify the elements. And he said that if you aggregate or if you average all the properties of hydrogen, all the 8 hydrogen, you will get properties of oxygen. Similarly, if you take an average of all the 6 hydrogen, you will get properties of carbon. But that was pretty vague, not accepted. Then the second one to attempt the classification of periodic table was Lavoisier. Okay, Antoine Lavoisier, which we also know him as a father of chemistry. Okay, so yes, we'll be talking about what? Antoine Lavoisier. Okay, he is also known as what? Father of chemistry. So according to Lavoisier, what he said that elements are basically classified as what? Metals and non-metals. That's it. Okay, he simply says that you can classify elements only in 2 terms, metals and non-metals. But yes, we know that this theory also got discarded because there is something known as metalloid that existed. So that's what I've written over here. This discovery was discarded because some elements have properties of both metal and non-metal, and they are known as metalloids. Okay. Yes, the next one was Dobereiner. I hope you know this thing. What does Dobereiner said that? Okay, Dobereiner said a law of triads. Okay, he gave what? Law of triads. In law of triads, what does it say? If you arrange element in increasing order of their periodic number, atomic mass number. Okay, if you arrange element in according to their increasing order of their mass number, then the average of first and the third atom, okay, average of the first and the third element will be, that is nothing but the atomic mass number average of the first and the third element will be the equal to mass number of the middle element, like this one. The atomic weight of the center element of each triads is the nearly equal to the average of the atomic weight of the other elements. To take an example, let us take aluminium, lithium, sodium, potassium. So what it says what atomic weight of lithium plus atomic weight of potassium will give you atomic weight of sodium. So lithium is 7, potassium is 39. If I take an average, it is divided by 2. Total you'll get is what? 23. And 23 is the average atomic weight of 23 is what? Average atomic weight of what? Sodium. Similarly, you can take this. Okay, these are also known as what? Triads. Dobereiner triads. Like for an example, let us prove for first one. So can I say that beryllium plus calcium divided by 2? What is beryllium equal to? 9 plus 40 by 2. That is equal to 49 by 2. That is equal to 24.5. Right? See, magnesium. It is 24. Magnesium is what? 24, and we are getting what? 24.5. And that's what the statement says. Law of triads. It is nearly equal to average of atomic weight of other elements. Clear? Sure. Perfect. So you can try it for any other as well. Okay, but yes, these are what? Dobereiner law of triads. They follow Dobereiner law of triads. Okay, the next one to attempt for the classification of element in the form of periodic table was Newland. Okay, and he gave Newland law of octaves. Okay, so yeah, next one. In 1865, an English chemist, Alexander Newland, made a next attempt in the classification of elements. Law of octaves. And he gave what? Law of octaves. It says that when the atomic weight of elements are arranged in increasing order, the properties of eighth element is similar to the first element. The property of every eighth element is equal to what? Similar to the first element. And he derived this analogy with what do we say? On the sound notes. Okay, like sa, re, ga, ma, pa, da, ni, sa, like that. Okay, clear? And this analogy, okay, this analogy suits well, but not for the entire periodic table. But yes, for some of the elements, yes, it suits well. Okay, but yes, there was also some of the problems that we are definitely going to discuss. So he compared the relationship of the first octave of music with 8 notes. Hence, it is also known as what? Newland's law of octave, like this. So what he said, the first and the eighth element will have the same property, right? As of now, we know that lithium, sodium, potassium, they all are alkali metals. Today we know it, but at that time he didn't know. But yes, his analogy suits well. That is C. Sa, re, ga, ma, pa, da, ni, and again comes sa. So that means the first and the eighth note of the music are same, right? And that's why he said that the first and the eighth element will be what? Same, having the same property. Yes, so that was what? Newland's law of octave, right? But the theory failed. Why? Because at that time there was no development of inert gases or noble gases, right? So ideally today we know that after fluorine what comes is neon, and if neon comes, so it will become Sa. So the first and the eighth element are not the same. The first and the eighth element are not the same. That is the first thing, because there was no development of what? Inert gases or noble gases. Secondly, this particular analogy is not applicable beyond calcium. Okay, beyond calcium you cannot apply it. So it is only applicable to atoms having low molecular or low atomic weight, but not the elements having high atomic weight. Okay, so that forms what? Its drawback. So the drawback is pretty much simple. What are the drawbacks? Wait a sec. Yeah. What is the drawback? Beyond calcium, repetition was not observed. Inert gases were not discovered at the time. The law is only applicable for lighter element. Clear? Sure. Any doubts? Any difficulties to anyone? Any doubts? Any difficulties to anyone? No one? Sure. Perfect. Let's move ahead. Okay. Now, coming upon to Lothar-Meyer curve. If you'll ask me, okay, if I want to give my opinion, I'll say that Lothar-Meyer curve, okay, he was one of the first scientists or chemists, you can say, to give you an exact, okay, he was the first one to give you an exact thing that was needed. But yes, he gave his classification in the form of curves, or basically in the form of graph. Okay, and that graph was not easy enough to understand. Okay, it was not easy enough to understand. That's why this particular concept or this particular law or this particular search, I can say, that is not popular. Okay, थोड़ा सा कैसा था, tedious था समझने के लिए, इसके लिए ज़्यादा पॉपुलर नहीं हुआ, वरना यस ये बेस्ट था. इसी के बेसिस पे मेंडलीव ने अपना पीरियोडिक टेबल दिया था. प्लीज मेक अ नोट ऑफ इट. ऑन द बेसिस ऑफ फाइंडिंग्स ऑफ लोथर-मेयर कर्व, मेंडलीव गेव इट्स पीरियोडिक टेबल, दैट इज मेंडलीव पीरियोडिक टेबल. तो देखते क्या है इसमें. In 1868, a German chemist, Lothar-Meyer, made the next attempt in the classification of elements. Right? He plotted the graph of atomic volume versus atomic mass. Okay? Atomic volume versus what? Atomic mass. He plotted a graph of that. Okay? Clear? Now, so atomic volume is equal to what? Gram atomic mass of element by density. Although you don't have to remember this thing. Okay, directly मैं क्या करूँगा, ग्राफ दिखाऊंगा तुम्हें, एंड इसके रिलेटेड सारे इंफॉर्मेशन जो भी चाहिए वो ऑब्वियसली हम डिस्कस करेंगे. सो लेट अस गो डायरेक्टली टू द ग्राफ. ओके, दैट इज दिस Lothar-Meyer curve, atomic volume versus atomic mass. So if you'll see, there are some circles, square, something that has been done. Right? Now let us discuss this thing. Now if you'll see, ध्यान से देखना, जिस रेड वाले सर्कल्स है, that is what? Lithium, sodium, potassium, rubidium, cesium. Can I say they all are alkali metals? Right? And अगर alkali metals को ध्यान से देखोगे तो सारे के सारे टॉप पे हैं. It is at the top. Okay? सारे के सारे क्या है? टॉप पे है. At the top, मतलब पहाड़ के एकदम टॉप पे, पीक पे है. Okay? Clear? Then see. Magnesium, ग्रीन कलर के सर्कल्स पे ध्यान दो. Calcium, स्ट्रॉन्शियम, बेरियम. ये वाला कैसे? स्लोप्स के नीचे आते वक्त है. ये वाला देखो, इवन बेरिलियम, सी इवन बेरिलियम, ओवर हियर मार्क करना रह गया. बेरिलियम स्लोप के नीचे आते वक्त है. ओके, व्हाइल कमिंग डिसेंडिंग पार्ट ऑफ दिस स्लोप. कैन यू सी दिस थिंग? ये क्या है? अल्कलाइन अर्थ मेटल. ऊपर क्या है? अल्कली मेटल. राइट? सो मतलब सबके पोजीशन एक ही जैसे है. देन सी क्लोरीन, ब्रोमीन, आयोडीन, असेंडिंग पार्ट ऑफ दिस स्लोप, मतलब एक ही पोजीशन पे है. गेटिंग द पॉइंट? दैट मीन्स लोथर-मेयर कर्व के हिसाब से भी अल्कली मेटल्स एक लाइन में आएंगे, अल्कलाइन अर्थ मेटल्स एक लाइन में आएंगे, हैलोजेंस एक लाइन में आएंगे. देन सी, कैन यू सी दिस? आयरन, कोबाल्ट, कॉपर, जिंक. कैन यू सी दिस? देन अगेन जिरकोनियम, मोलिब्डेनम, रुथेनियम, कैडमियम, टिन, इंडियम. कैन यू सी दिस? एंटीमनी. सो दीज आर व्हाट? इफ यू सी दिस थिंग केयरफुली, अगर ये वाला ध्यान से देखोगे तो दिस फॉर्म द मिड ऑफ द पीरियोडिक टेबल, दैट इज नथिंग बट डी ब्लॉक एलिमेंट. एंड जैसे जैसे बढ़ते जाएगा ये, इसका जो नीचे वाला कर्व है वो भी बढ़ते जाएगा, बिकॉज डी ब्लॉक विल स्टार्ट कमिंग ओवर यू. गेटिंग द पॉइंट? श्योर. सो दैट वाज ओके. दिस पर्टिकुलर graph was given by whom? Lothar Meyer. And since this graph was given by Lothar Meyer, that's why I'm a fan of Lothar Meyer, because he was the first one to actually classify the element properly. And his findings forms the basis of what? Mendeleev periodic table. Clear? Sure. Any doubts, any difficulties, guys? Any doubts? Any one of you, any doubts, any difficulties? No one? Sure? Got it? Perfect. Sure. आगे बढ़ते हैं. Now, proceeding further. So, what are the things that we observed? The element having similar properties are in the same position of the curve. For example, alkali metals like lithium, sodium, potassium, rubidium, cesium are present at the peak of the curve. Discuss किए हैं हमने ये वाले भी. Beryllium, magnesium, calcium, strontium are a descending part of the curve. Fluorine, bromine, iodine are on the ascending part of the curve. Most of the transition elements are lying at the broader minima of the curve. Got it? ये सारी चीजें हमने discuss किए. Then atomic volume of the element changes periodically in period. That is, it initially decreases and then increases with a broader minima. Okay, so atomic volume की बात चल रही है यहाँ पे. And the atomic volume increases in the group. Okay, atomic volume increases in the group. Okay, so Lothar Meyer proposed that the physical properties of elements are the periodic function of their atomic weight, and this forms the basis of Mendeleev's periodic table, as I said you. Okay, done. Anyone having any doubts, any difficulties? Anyone having any doubts, any difficulties? Sure, no one? No one, guys? Perfect. Next, talking about Mendeleev's periodic table. Okay, he was a Russian chemist, Dmitry Mendeleev, proposed the periodic law. Okay, which states the same thing. The property, that is physical and chemical properties of the elements, are periodic function of their atomic weight. Okay, it is the function of their what? Atomic weight. That means he arranged all the elements on the basis of what? Atomic weight. But yes, we must make sure one thing, that he didn't stuck to this particular point कि नहीं atomic weight से ही arrange करना है. Okay, कहीं पे उसने priority change की atomic weight की and chemical properties को priority दी. Okay, clear? So we'll discuss that thing as well. So yes, this is what the periodic table. Okay, this is what the entire periodic table look like. Mendeleev's periodic table. Clear? Sure. Clear? Perfect. So yeah, if you see it carefully, इसमें जो ये वाली series है, okay, sorry, not this one. I am talking about the zero series. Okay, it was added later. Okay, ये बाद में ऐड किया गया था. मेंडलीव के टाइम पे ये ऐड नहीं किया गया था. So ideally it consists of how many vertical columns? So it is 1, 2, 3, 4, 5, 6, 7, 8. Okay, how many horizontal rows it has? 1, 2, 3, 4, 5, 6, 7. There were total 7, right? So horizontal, wait a sec, yeah, so horizontal periods. Okay, please remember this thing, and we say this thing as HP laptop basically, if you want to remember. Okay, HP is what? Horizontal period, and vertical is what? Groups. So please make a note of it. Clear? Sure. Let's see what are the important pointers of this thing. So in 1871, Mendeleev published his periodic table, as it consists of how many elements? Okay, it consisted of 63 elements, and inert gases were not included because they were not discovered at that time. The elements were arranged in 7 horizontal rows, okay, called periods, Okay, and 8 vertical columns known as groups. Okay, clear? Mendeleev table was later modified after the discovery of inert gas of several elements. Okay, so inert gas was added to 0 group. That's what I said. It was added later. Okay, clear? Next, Mendeleev not only left the vacant spaces for undiscovered element, but also predicted the property of, their property as well. Like he said that Eka silicon will have the property of germanium. They both are what semiconductors. Eka aluminium will be having the property of gallium, belongs to the same group, and Eka boron as scandium. Clear? Sure. The vertical column known as group were further divided into 2 subgroups, namely A and B, to accommodate the element with different properties. Okay. Coming upon to the further part, the study of the properties of elements becomes more systematic. Okay, periodic table आने के बाद क्या हुआ? Study of the periodic table will become more systematic and easier. Okay, clear? Sure. Now, there were vacant spaces left in Mendeleev's periodic table for which guidance of discovery of new elements was found. Okay, clear? इस पॉइंट का बेसिक मतलब क्या है? जो भी स्पेस मेंडलीव पीरियोडिक टेबल में रह गया था, दैट गेव एन अपॉर्चुनिटी फॉर ऑल द साइंटिस्ट और द रिसर्चर्स कि वो जाके उस पर्टिकुलर स्पेस को फिल करे बाय डिस्कवरिंग दैट पर्टिकुलर एलिमेंट. क्लियर? श्योर? एनी डाउट्स टू एनीवन ऑफ यू? नो वन? श्योर? परफेक्ट. नाउ the rectification of atomic weight of several elements was done by Mendeleev. Please make a note of it. Okay, clear? For an example, if my memory serves right, या शायद से कहीं ना slides में होगा भी, boron. Okay, it's what we say. Boron atomic weight was considered to be boron or beryllium, if I'm not mistaken. Its atomic weight was considered to be 11, but actually rectified and made it as 9. Okay, so it might be there somewhere. Yeah, exactly here. See, beryllium and aluminium show similar properties. Okay, and this is known as beryllium and aluminium shows similar properties, and this is known as what? Diagonal relationship. This is known as what? This is known as what? Diagonal relationship. Okay, and due to this diagonal relationship, beryllium was considered to have a valency of 3, and if we'll take that valency of 3, its atomic weight comes out to be this. Okay, but Mendeleev found out that it's the valency of beryllium is how much? 2, and he rectified the atomic weight from 13 to 13.5 to 9. So basically I was wrong over here. It was around 13. Okay, clear? Sure. The another list of elements whose atomic mass was corrected by Mendeleev is this: beryllium, indium, gold, platinum, vanadium. Okay, try to remember. I don't think so it will be asked in the examination, but yes, I'll recommend you to remember it. Okay, clear? Next. Now, what was the demerit? This demerit still exists. The position of hydrogen is still uncertain, like it is placed in the middle of the periodic table, but yes, that is an uncertain position. In certain pair of elements, the increasing order of atomic mass was not followed or obeyed. Like argon came before potassium. Okay, ideally potassium should be first, then should be argon, but it was not followed. Beryllium came before iodine. Okay, similarly cobalt came before nickel, something like that. Okay. Even though isotopes have different atomic masses, yet they do not. Okay, different atomic masses. Isotopes have what? Different atomic masses. They do not have position in the periodic table. Like according to Mendeleev, it was arranged in order of their what? Atomic masses. And since isotopes have different atomic masses, so like basically carbon, for example, talking about carbon 12. Carbon 13, carbon 14. So there has to be 4 position. Okay, sorry, not 4. There has to be 3 position in the Mendeleev periodic table for this thing, because their atomic mass keeps on increasing, but still they do not find any position. Okay, clear? Next, the classification of metals and non-metals is not done in this table. Okay, from Mendeleev periodic table, you cannot define what is metal, what is non-metal, and what is metalloid. Okay, and last one, in 8th group 3 elements were placed together. Clear? So this was what demerits of what Mendeleev periodic table. Now talking about Moseley, Henry Moseley. Okay, he was the scientist who actually gave us an idea that the physical and the chemical properties of an element are not the periodic function of atomic weight. He said that it is not the periodic function of atomic weight, rather it is the periodic function of atomic number. Okay, clear? Sure. So that was okay. This is according to what periodic law. Okay, it is the periodic function of the atomic weight. But according to Moseley, modern periodic law says that it is the periodic function of their atomic number. Okay, so he did a very simple experiment. Okay, he did a very simple experiment that is obviously discussed in details in atomic structure. But yes, after that experiment, what was found to be is what this Moseley equation. And when he plotted graph, okay, when he plotted graph of root of frequency versus atomic number, okay, something like this. Okay, so here it is what root of frequency, and here it is atomic number. Okay, and at the same time, if you plot a graph of frequency and atomic mass number, okay, he found that there isn't a straight line. Okay, in both the case he got straight line, but in case of mass number, most of the atoms, okay, most of the atoms was on the line, but not all. Okay, most of the points were on the line, but not all. But the moment he plotted the same thing with respect to atomic number, he found that each and every point lie on this line. Okay, there was no deviation. It was simply on this line. Okay, clear? So yeah, that's what he did. That's what he did. And on the basis of that, he formed a periodic table and he gave modern periodic law, which state that the physical and the chemical properties of the element are the periodic function of their atomic number. Is the periodic function of their what? Atomic number. Talking about some of the features of periodic table, it consists of 7 horizontal rows known as periods. I have already given you the shortcut to remember HP. Okay, and the second one is vertical columns known as what? Group. There were total 18 vertical columns. They are known as what? Group. So VG. The entire periodic table are classified into blocks. It consists of 4 blocks, that is S, P, D, S block element. S block element, you know that when the last electron enters in S orbital, it is known as S block. Similarly, P block, D block and S block elements. Okay, so we have different discussion for all this particular block. Clear? Sure. Now, proceeding further, this is how this modern periodic table look like. Okay, this is how the modern periodic table look like. Now, if I wanted to show you the rows, so see, this is the first period, second, third, fourth, fifth, sixth and seventh. Okay, this is lanthanide and this is actinide. These are not the new period, it is a part of this group. Okay, then that total 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and this is 18. Okay, this entire table, this group 1 and 2. Okay, this group 1 and 2 is known as S block. This is entirely known as what? D block. This is entirely known as what? P block. And this two are known as what? F block elements. Okay, clear? So these are what? These are the basic features of what? Periodic table. Clear? Sure? Perfect. Proceeding further. Question. Okay. It came in 2017. Okay. It came in what? 2017. The question says that the element Z is equal to 114 has been discovered recently. It belongs to which of the following group and electronic configuration? Okay, so very simple guys. Trust me on this thing. There are two ways to solve this thing. Either you can write the entire electronic configuration, or you can use a different sort of a thing, what I use. See, I know that as a matter of fact, 118 belongs to 18th group. Similarly, 117, 116, 115 and 114. So, okay, 18th group, then this one will be 17th, this one will be 16th, this one will be 15th, and this one will be 14th group. 14th group, if I am not mistaken, is carbon family. 14th group is what? Belongs to what? Carbon family. As simple as that. Okay, you don't need to think. You can mark directly answer as carbon family, because all the families are different. If you want to write down its electronic configuration, you can go ahead and write it down. Okay, but yes, this is the best way to approach it. Okay, 114, it comes from the 14th group. Okay, 14th group is carbon family. No doubtedly, it is carbon family, the right answer. Okay, next. An atom has electronic configuration this. You will place it N. Now, how to solve this particular question? It has this electronic configuration. You need to find the place. You need to see. Okay, the first thing is you need to see where is the last electron entering. Okay, so the last electron that enters in d orbital, because it is incomplete. Rest all are complete. That means, okay, d orbital is incomplete. That means the last electron enters in d block element. That means it belongs. This particular thing belongs from d block. And the moment you remember D block, you should remember from 3 to 12. Okay, from 3 to 12 belongs to what? D block. Okay, that means 3rd to 12th group. Okay, so yes, 15th can be the answer, but 5th can be the answer, but 15th cannot be the answer. 2nd group cannot be the answer. 3rd and 5th can be the answer. Okay, clear? But 3rd group means what? 3rd group means what? How many electrons? 3rd group means what? It is like 2 s orbitals are there and one d orbital. But total there are how many d orbitals? 3. 2 s orbital plus 3 d orbital. Total gives you what? 5. So it belongs to 5th group. This is not the answer. Okay, clear? So whenever last electron enters in d orbital, the case is very much simple. What you have to do is you have to add number of electrons in d orbital. With some exception, you can use this rule. Okay, you can use this formula. Number of electron in d orbital plus, okay, number of electron in d orbital plus 2. That will give you what? The position in terms of group. So 3 plus 2 is what? 5th. Similarly, suppose if the electron has entered in the p orbital, so what you have to do? Number of electron in p orbital plus 12. Number of electron in p orbital plus 12. If it is enters in f orbital, life becomes pretty much simple because their group is fixed, that is 3rd. Clear? Sure. If last electron enters in 4f, it belongs to 6th period. If it belongs to 5f, if the last electron enters in 5f orbital, that means it belongs to 7th period. As simple as that. So yes, these are some of the tricks that you should know. Okay, clear? Next, nomenclature. Okay, this is one of the questions that can come in the examination, and that has came in the examination. Okay, so please make a note of it. And I'll give you, and it's my recommendation to all of you that please try to remember all the elements name from 101 to 118, including the recent discoveries. Okay, so by using this thing, let us mark some of the atomic IUPAC nomenclature. Okay, so this table I am not going to fill. I am just going to fill some of it. Rest you can just fill it. Okay, so name according to IUPAC. Okay, so let's see 1. Okay, so 1 is what over here? If you'll see 1 is what? 1 is what? Un. Okay, so it is un. Plus O will be nil. Okay, that is 0 will be what? Nil. So nil. plus 1 is again Neum. So what will be the entire name? What will be the entire name? It will be Nil Neum. Right? Similarly, let us try for 106. So it will be wait. It will be Nil. Then what does 6 stands for? Hex. So Nil Hex Neum. Okay, clear? So yeah, this is how you can write just by using the abbreviation which is mentioned over here. For 0 it is nil, for 1 it is for 2 it is bi, for 3 tri, 4 quad, 5 pent, 6 hex, 7 hept, 8 oct, and 9 is non. It is not there, it is 9 is non, that has been missing, right? Clear? And these are the abbreviations. Okay, clear? So yeah, this you can just fill it by yourself. I hope you can do it by yourself. Okay, so just take this thing as your homework. Try to fill it. Okay, but yes, what I have given is the name. If you see, okay, I have given you the name. You have to try to remember this thing. Why I am saying so? Because one of the questions that appear in NEET 2020. This is a reason. Okay, this is the reason why I am telling you. Please try to remember this thing. Okay, where? Let us start. It is nil. Means what? Means what? 1. Nil is 0 and is 1. Okay, so nil, that is 101 is Mendeleev. That is true. Okay, we have to find out the incorrect match. So this is correct match, and hence that's not the right answer. Nil tri. So nil tri is Laurentium. That is also true. If you remember it, you can easily mark it. So hence not the right answer, because this 2 match is correct. Nil Hex, that is Seaborgium. We have just seen this thing, it is correct, and hence that will be the right answer, D. It is Darmistidium. If I am not mistaken, this is not Darmistidium, it is 110. Let us just check. 110 is Darmistidium. Let us check. 110 is Darmistidium. Yes, as I was saying, 110 is what? Darmistidium. Okay, and 111 is Rhongtinium. Okay, so yes, that is the right answer, because that's an incorrect match. Clear? Sure. Perfect. Let's proceed further. Talking about the electronic configuration period, this is the electronic configuration in the entire period. No need to discuss this thing in details. Yeah, group wise electronic configuration, this you should try to remember. For the first group, the electronic configuration will be NS1. The second group, the last. Okay, this is nothing but the configuration, that is 7s2. Then it is NS2 NP1, NP2, NP3, 4, 5 and 6. Talking about this entire D block element has general electronic configuration as N-1, D1 to 10 and NS0 to 2. Okay, clear? And that's why, since the electron enters in the penultimate, since the last electron enters in the penultimate orbit, it is also known as what? Inert, transition element. It is also known as what? Transition element. The reason of transition element, because it gives a bridge between S and P block element. Okay, it gives us the what? The bridge between S and P block element. Clear? Coming upon to the last one, F block element. It is N to N-2, F 0 to 14, N-1, D 1 to 10 and NS 0 to 2. Clear? Sure. Next, proceeding further. Okay, this is the entire blocks, if you'll say. Group 1 and 2 comes under what? S block. 13 to 18 comes under P block. In that, one important thing, 18th is what? Noble gas. 3 to 10 comes under what? D block, and this entire thing is what? F block. The electronic configuration is already discussed. Next, talking about the types of element, S and P block elements are known as what? Representative. Except group 18. Group 18 is known as what? Noble gas. This is known as transition elements, and this is known as inert transition elements. Okay, clear? Sure. Now, Let's proceed further. Talking about metals, almost 90% of the entire periodic table is what metals. Okay, if you'll see it over here carefully, okay, this entire stuff till over here, this one, okay, they all are metals. This entire portion that you can see, they all are what? Metals. Okay, then next, this green segment that you are seeing, this green segment, this one, okay, they are metalloid. They comes under segment of what? Metalloid. Whereas this last one, okay, they are non-metals. They are what? Non-metals. So yes, most of the periodic table is been occupied by what? Metals. Clear? Sure. Perfect. Now, periodicity in elements. The recurrence of similar properties of the elements after certain regular interval when they are arranged in increasing order of their atomic number is known as what? Periodicity. Okay. Reading further. Now, what is the cause of periodicity? The cause of periodicity is electronic configuration. Repetition of what? Electronic configuration. Like, see, 1s1, 2s1, 3s1, 4s1, 5s1, 6s1. It's just the period number that has changed, but the electronic configuration still remains same. S1, 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 and S1. Clear? Sure. So this is what cause of periodicity. This is what cause of what? Periodicity. Clear? Perfect. Now, talking about trends in periodicity. Okay, talking about what? Trends in periodicity. We'll wait for 2-3 minutes and then we'll start with what? Trends in periodicity. Okay. So yeah, let's wait for some time and then we'll quickly get started. Okay. Okay, so let's get started, guys, with the trends in periodicity. Okay, so this trends in periodicity forms the most important segment of periodic table. Till now, whatever we discuss, yes, there are possibilities that the question can come from that segment. But yes, in this segment, yes, this is the most important thing that I should say you that to try to understand. Okay, so trends in periodicity can be studied in two ways. First one is atomic property, and the second one is molecular property. Okay, out of all these trends, the only molecular property that we are going to study is atomic radii. Rest we are not going to study. Okay, rest we are not studying. And in atomic property, we are studying all. Okay, we are going to study all. Clear? Sure. So let us get started. Okay, why we need to study atomic radii in terms of molecular property? Because these atoms are really very small. Okay, and to get the exact radius of that particular atom is very difficult. Okay, and since these atoms, most of the atoms exist as, you know, as a dimolecule, or they are at least attached to one another. That's why we study them as a periodic property. Rest all we are going to study as an atomic property. Okay, what is an atomic property? That can be explained only by one atom. Whereas what is molecular property? That cannot be explained. Okay, it is B, that cannot be explained on the basis of one atom. So let's get started. Okay, now let's get started. And the first thing that we are going to discuss is the shielding effect, also known as screening effect. Okay, to understand the shielding effect or a screening effect, you need to focus on this model first, that is single electron species. Okay, a single electron model. Wait a sec. So single electron species. Now, if I talk about the single electron species, can I say that, okay, what exists between this nucleus which you are seeing over here, what exists between this nucleus and this electron over here is just the force of attraction. That means this electron is experiencing all the force, okay, all the positive charge or all the force of attraction given by nucleus. So all the attractive forces is being experienced by this electron. If it is a single electron model, okay, if it is what, only a single electron model. But what about if the molecule or if the atom is not a single electron? Because we know that in periodic table, the only atom that has only one electron in its atom is hydrogen. Rest all are what? Rest all are what? Multi-electronic species or multi-electronic model. Okay, and this is the example of what? Multi-electronic model. Okay, clear? Now, yes, obviously what exists here, we are going to fixate on the outermost electron, this, which I am going to do as a box, the bigger one. Okay, yes, one thing that exists is this force of attraction that you can see in the forms of blue line. Force of attraction hai, no doubt in that. Force of attraction is still there. That means this nucleus is still exerting some force of attraction. But can I say that this electron will also face some repulsion between the inner electrons which are present, right? So ये जितने भी electrons हैं यहाँ पे, like this, like this, like this, all this electron what will do? They will try to have, or they will repel the outermost electron. So that what exists is the force of repulsion. Okay, and ये force of repulsion होने के वजह से क्या पूरा का पूरा nuclear charge इस electron पे apply हो रहा है? Answer is no. This nuclear charge is not completely pulling the electron as compared to this particular single electronic model where there is no force of repulsion. So can I say that the force of attraction experienced by this electron will be less as compared to the actual, or what is expected? The actual force of attraction that is experienced by this electron will be less as compared to the expected force of attraction. Okay, and this difference is known as what? Shielding effect. That means what happens? This electron, this inner core electrons are shielding the outermost shell electron from nucleus, or they are screening, they are acting as a screen, due to which this nucleus will not be able to pull the electron with its entire strength, and that is known as what? Shielding effect or screening effect. Clear? Sure. Like what I am trying to say is this: the repulsion caused by the inertial electron decrease the net Okay, repulsion caused by inner shell electron decrease the net force of attraction between nucleus and the valence shell electron. This is the first thing, and hence the decrease in force of attraction caused by inner shell electron between nucleus and valence shell electron is known as screening effect or shielding effect. Okay, this decrease in the what force of attraction is known as what screening effect or shielding effect. Clear? Sure. So yeah, this is the concept of screening effect or shielding effect. Now, proceeding further, if I talk about screening effect and shielding effect in terms of orbitals, it decreases from s block to f block. S block acts as a very good shielding, or its screening effect or its shielding effect is highest. I'll explain you why. But P block bit decreases, D block it decreases more, and F block it is pathetic. It is very bad, very poor shielding effect. Now exactly why does that thing happen? Now, just to imagine that, let us assume this thing as a football. Although it looks like a football, okay, it is like a football only. It's like a sphere. Inside this football there is a nucleus present. Okay, inside the hollow part of that football, nucleus is present right exactly at the center. Can I say that since S block or this S orbital is spherically symmetrical from entire direction, so it is shielding the nuclear force of attraction from every direction, right? It's like you have kept the positive charge inside, and then you have covered with a sphere, and the electron is present outside of that sphere. So can I say that that sphere is having a strong potential to stop the force of attraction toward itself? That means the final force of attraction or the net force of attraction that has been experienced by the valence shell electron will decrease, right? When the inner shell electrons are present in S block. But you will see if P block is a bit dispersed. Its electronic cloud is in this direction, or it 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 is in this direction. So if it is not surrounding the entire like sphere, okay, not from everywhere, there are some loopholes. See, here. So yes, definitely it will not shield it properly. It will not shield the nuclear force of attraction that in that great way as compared to S block, right? So yes, it is not diffused, but yes, it has been a bit diffused. But if I talk about D block, it is more diffuse as compared to what P block, and hence its shielding effect still decreases. And F block is highly diffused structure, and since it is highly diffused structure, it will have a very poor shielding effect, and hence shielding effect decreases from S, P, D and F. Clear? Sure. So this is okay. This is known as what? Screening effect or shielding effect. So please remember, S block will have maximum shielding effect, right? And hence the net force of attraction, which is also known as effective nuclear charge, okay, which is also known as what? Effective nuclear charge will be less. Okay, effective nuclear charge will be less if the electron is present outside of the what? S orbital, as compared to P, as compared to D, and as compared to F. That means if F orbitals are present in midway or in inner core electron, then the effective nuclear charge will increase on the last electron. If S orbital is present as an inner core electron, its effective nuclear charge on the last electron will decrease. Okay, Z effective decreases, but shielding effect increases. Okay, again I'll write Z effective decreases, but screening effect, okay, increases. Clear? If we go from this direction. Clear? Sure. Now, what is screening effect or shielding effect? Okay, it is the net force of attraction experienced by a particular electron. Okay, net force of attraction experienced by a particular electron is termed as what? Effective nuclear charge. That means the nuclear charge experienced by this electron, only one electron in the outermost shell, is known as what? Z effective. Effective nuclear charge. Clear? Sure. Now, So yeah, that is all about what effective nuclear charge. Effective nuclear charge can be calculated by, okay, known as what? Slater's rule. Okay, effective nuclear charge can be calculated by what? Slater's rule. Okay, so yeah, although in our syllabus we don't have Slater's rule, okay, we definitely don't have Slater's rule, so we don't have to take care about all of it. Okay, now proceeding further, in general, variation of effective nuclear charge in periodic tables as we move from left to right. Okay, as we move from left to right, what happens? See, nucleus, first electron, so there are 2 electrons. Let us go for the second period where there are 8 electrons going to be filled. Now, if I talk about lithium, okay, so proton and electron. Okay, if I talk about this lithium, there are 3 protons, 3 electrons. That means 3 proton over here, that means it has 3 protonic charge and 3 electrons. Now, if I talk about beryllium, let me mark 1 electron over here. Beryllium, 4 proton, that means the nuclear charge has increased, and 4 electron. Right? Now see, the repulsion has increased. Okay, if there was only 1 electron, if there is no electron, no repulsion. But if there is 1 electron present, that means the repulsion has increased. But what about what about force of attraction, or what about nuclear charge? Nuclear charge has also what increased. Right? Clear? Then what about Z effective? Okay, what about Z effective? Z effective what increases? Because the electrons are adding at what? Electrons are adding in what? In the same shell. Again, 5 electron. Again, 6 electron. That means the nuclear charge keeps on increasing, but still the electrons are getting added in the same shell at a point. Okay, its repulsion remains same, because adding an electron in the same shell is not going to increase the repulsion, right? So can I say that the repulsion remains same, but the nuclear charge keeps on increasing, and hence the what we say, the net force of attraction experienced by the valence shell electron also increases, and that is the reason why effective nuclear charge increases from left to right. That means from lithium to neon, the effective nuclear charge increases, and that can be shown in this way. See the values, it keeps on increasing. Okay, clear? So across the period, effective nuclear charge increases. Clear? And please make a note of it, effective nuclear charge increases from left to right or across the period, because this will be very much helpful in terms of understanding atomic radius, ionization enthalpy, electron gain enthalpy, electronegativity and whatnot. Okay, clear? So please make a note of it. Okay guys, sure. Next, if I talk about group, the values itself suggest that, okay, it first increases and then it almost remains constant. It does not change. Okay, so it increases slightly or remains same. So across the group it doesn't matter. Why? Because if you come from lithium to sodium, okay, from lithium to sodium there are 2 shells over here. Here there is 3 shells. Then sodium to potassium, 4 shell. Potassium to rubidium, 5 shell. That means the number of shell keeps on increasing. And since the number of shell keeps on increasing, the distance between the nucleus and the outermost shell electron also increases. And since the distance increases, the effective nuclear charge, okay, it's been compensated, okay, by the nuclear charge. So that's why it almost remains same or it increases slightly. Clear? Sure. Any doubts, any difficulties to any one of you? Any doubts, any difficulties to any one of you? No? Perfect. Let's proceed further. Now, talking about atomic radius. Okay. Now, what is atomic radius? It is a distance between the center of the nucleus to the valence shell electron, or to the what we say, it is a distance between the center of the nucleus to the probability of finding the electron, that is psi square. Okay, so that's what I've written over here, the distance between the nucleus to the valence shell electron, or to the point at which the probability of finding the electron is maximum, is known as what? Atomic radius. Okay, but determination of atomic radius is really difficult, as I said you at the start as well. Why? Most of the element present in the nature does not exist as atomic state. They exist as a molecule or a combined state. Second, atoms are very small and do not have any defined boundaries. Last, due to wave nature of electron, okay, since it is a wave nature, again becomes very difficult to calculate its atomic radii. Due to all above reason, atomic radii of any atom is always calculated in the bonded state. Okay, and there are three types of atoms or atomic radii that we define. The first one is covalent radii. The first one is what? Covalent radii. This one. Then the second one is metallic radii, and the third one is van der Waals radii. Van der Waals radii is completely applicable for noble gases. Metallic radii are for metals. Okay, and covalent radii are for what? Non-metals basically. Okay, out of all, covalent radii will be the, okay, if I want to show you with the help of a diagram, let me help you out to show you with the help of a diagram. If I want to mark covalent radius, it is like this. Since it is formed by overlapping, this is the distance. Okay, so this will be the distance. If I talk about metallic radii, they do not merge inside. Okay, their surfaces are touching like this. So this is the distance. And if I talk about van der Waals, it is the nearest atomic distance, something like this. So distance by 2, or diameter by 2, you can say that. Clear? So you can clearly say that van der Waals radius, okay, van der Waals radius, that is RV, will have maximum radii as compared to RM, that is metallic radii, and as compared to covalent radii. So please make a note of it. Okay, this will be helpful. Now, proceeding further, that's the same thing I have written over here. Okay, that's the same thing I have written over here. See, van der Waals radii, okay, for any given element, van der Waals radii is more than the metallic radii and is more than the covalent radii. Clear? Sure. Okay. Second, RV is defined only in solid state. RV is not applicable to metals. For inert gases, only RV is defined. That is van der Waals radius. Now, proceeding further, and let us discuss exactly what is the trend. The trend in the atomic radii is, if you go from left to right, is effective nuclear charge increases. And since effective nuclear charge increases, that means the force of attraction on the outermost shell electron also increases. And since the force of attraction increases, they will try to come close as possible. And since the outermost shell electron and the nucleus try to come as close as possible, their atomic radius decreases as we go from left to right. Okay, so across the period, the atomic radius decreases. But from top to bottom, what happens? In top to bottom, the effective nuclear charge slightly increases or it remains the same. In both the cases, can I say that the number of shell keeps on increasing? And since the number of shell keeps on increasing, what happens? Since the number of shell keeps on increasing, what happens? Its atomic radii increases. Yes, there are some ambiguity. We are going to discuss that ambiguity as well. But in general, from top to bottom, their atomic radius increases. Clear? So what is the general trend? From left to right, atomic radii decreases. From top to bottom, atomic radius increases. Clear? Sure. Now, talking about this thing. First period. Okay, if I talk about first period, that is this. Okay. Okay, let us talk about the first period. So if I talk about the first period, hydrogen and helium is more. Why? Due to van der Waals radius. Because we know that helium is inert gas. Okay, we know that helium is what? Inert gas. And for inert gas, only RV is defined. Okay, if I talk about the period number 2, okay, in this thing, if all the radii is calculated in RV, that means all the given radius is calculated in RV, then see, then the importance of neon is gone. Right, since all are calculated in RV, first thing, that means all are van der Waals radius. Van der Waals radius something like this. They are not bonded. So obviously all the radius are mentioned in what? Van der Waals radius. So what happens from left to right? Left to right, the Z effective increases and hence the radius will decrease, right? So lithium will be having the maximum size as compared to neon when all the radii are given in RV. But suppose if all the radii is not calculated in RV, this not is missing over here, is not calculated in RV, then what you are going to do? Then normally metals will be RM, non-metal will be RC, that is covalent radii, and what we say, inert gas will be the van der Waals radius. And since van der Waals radius will be maximum in their own period, neon comes first. Because of what? Because of what? Van der Waals radius. Because neon, you cannot calculate atomic radius of neon in what we say, metallic radius or covalent radius. You have to calculate neon as an van der Waals radius. That's why neon comes first and rest the entire trend remains the same. See, the entire trend remains the same. In the third period also, if all the radii is calculated in RV, then sodium will be the maximum and argon will be the least. But if all the radii is not, this not is again missing over here, is not calculated in RV, then argon will be the maximum, rest all trend will remain the same. Clear? Sure? Any doubts? Any difficulties to any one of you? Any doubts, any difficulties to any one of you? Sure? Any doubts, any difficulties? No one? Sure. Perfect. Next. Let's proceed further. Let's proceed further. Okay. Now, there are some exceptions. Okay. There are some exceptions. In D block, okay, this is very much important. In D block, if you'll see, the general trend is decreasing only. Generally, it keeps on decreasing, but yes, it is not completely decreasing. What happens is, from here to here, see, from here to here, Z it decreases. Okay, sorry, not till here. Till here it decreases. Then again it increases from here. Almost remains same, and then at the end increasing. Okay, so this first trend is attributed to Z effective. Its effective nuclear charge keeps on increasing and hence the size keeps on decreasing. Then all of a sudden there is an increase. All of a sudden there is an increase in what? Atomic radii. This is due to the repulsion. This is due to a repulsion in pairing of electron. The repulsion caused by pairing of electron, we can say. Okay, repulsion caused by pairing of electron. Clear? Repulsion caused by what? Pairing of electron. Clear? So that is the reason in D block element. Okay. Now, coming to the next point of it, that is 13th group. 13th group shows the ambiguity like normally it should keep on decreasing, as we know that from top to bottom the number of shell keeps on increasing and hence the atomic radii should keep on increasing, but that doesn't happen. Okay, if you'll see between aluminium and gallium, gallium should have more size as compared to aluminium, but that's certainly not the case. Aluminium has more size than the gallium. Why? Due to something known as transition contraction or DD contraction. What happens over here is from aluminium to gallium, d orbital comes into the picture. From aluminium to gallium, okay, what fills this? 3d orbitals. Okay, 3d orbital fills. Okay, and since this 3d orbital has a very poor shielding effect, okay, I said you as a start, this has poor shielding effect. Okay, and since it has what? A very poor shielding effect, that is the reason, and since it has a very poor shielding effect, we can say that its Z effective increases. And since Z effective increases, gallium size decreases. Clear? Sure. Got it. So that is the case between aluminium and gallium. Ideally, it should be boron, then aluminium, then gallium, then indium, and then thorium. But that is not right. Ideally, this should be there because from top to bottom it keeps on increasing. So what the first change that occurs over here is sorry, I did it wrong. Wait. It should be like this, right? But the first change that occurs is boron. Obviously, it is smallest one. Then comes gallium, and then comes aluminium. Second, if you'll see this one, okay, if you'll see their size almost remains the same. 167 and 170 picometer, they are almost the same size. Now, for what purpose that happens? Because from indium to thorium, what comes is lanthanoid contraction. What is lanthanoid contraction? It is due to the filling of f orbital. Okay, due to what? Filling of f orbital. Their size, again, f orbital means what? Very poor shielding effect, and since it is having a very poor shielding effect, simply means what? It has a very poor shielding effect, since simply means what? Its Z effective increases, and its Z effective increases so much that, because see, f orbital means there are total 14 electrons added in f orbital. That means, can I say that 14 nuclear charge is also added? That is nothing but proton. So that means the nuclear charge has increased rapidly, and its repulsive forces or the shielding effect has decreases. Because of its poor shielding effect, its size almost becomes same, although they are having a different number of shells. Okay, clear? Sure. And one more important thing, please make a note of it. Gallium is the only element, okay, gallium is the only element in the entire periodic table which experience DD contraction or transition contraction. Except gallium, all D block elements shows transition contraction. Again, I'll repeat. Except gallium, all D block elements shows transition contraction, but apart from D block, the only element which experiences contraction is gallium. Okay, because if you'll see in carbon family, just after gallium, if you'll see in carbon family, you'll find that they do not experience any transition contraction. Yes, lanthanide and actinide contraction will still remain, but transition contraction is only experienced in gallium. Clear? Sure. So yeah, that was atomic radii trend. Now, talking about again exceptions in D block. See, ideally what should be the case? From scandium, ytterbium, lanthanum, we know that it should keep on increasing like this. Okay, it increases as well. Okay, generally it keeps on increasing. But if I talk about fourth group, normally what should happen? It should increase, but it is found that this zirconium and hafnium has almost same atomic size. They have almost what? Same atomic size. And not only this, from 5th group to 12th group. Okay, from 4th to 12th group. I'm talking about from 4th to 12th group. Okay, this order still remains the same. That means from 4th to 12th, 5th and 6th period element has similar atomic radii. Okay, it has what? Similar atomic radii. Please make a note of it. Right, like zirconium and hafnium is the same thing, right? In the same way. Got it? Clear? Sure. So yeah, please make a note of it. Very important part. Then, talking about ionic radius, but first of all, what is an ion? An ion is something which is formed by loss or gain of electron. So the species formed by either gain or loss of electron from their valence shell is termed as what? Ions. They are further classified as cations and anions. Cation means loss of electron, anion means gain of electron. Now, since electron has been lost, the nuclear charge remains the same, but since electron is lost, the repulsion decreases and hence effective nuclear charge increases. So in cations, if you form a cation, Z effective will increase. Okay, let us mark over here. Or I have already written, yes, I have already written Z effective increases. And for anion, Z effective decreases. And since Z effective increases, cation, ionic radii decreases, whereas anion, ionic radii increases. That means for a given atom A, its cation will have less ionic radii and its anion will have more ionic radii. Okay, and now it is very much easy to understand. If the positive charge keeps on increasing, that means +1, +2, +3, then we know that the size keeps on decreasing because the nuclear charge is increasing. That means as we lose more and more electron, its ionic radii will keep on decreasing. Similarly, if negative charge keeps on increasing, that means more and more electron is getting added, and since more and more electron is getting added, due to the repulsion, its size will keep on increasing. Okay, clear? Sure. So yeah, proceeding further from that point. Now, the ionic radii studies revealed that, as I already said, radius of cation is less than the parent atom, whereas radius of anion is more than the parent atom, and this is the concept that I have just shared it with you. Okay, clear? Next, if the number of shell increases, then the ionic radii increases. That is, ionic radii increases down the group. That means from top to bottom, the ionic radii keeps on increasing. Like hydrogen plus is the smallest and cesium is the highest. Similarly, see, beryllium is small, barium is large. Okay. Now, F minus is small, I minus is big, O2 minus, polonium minus. If the charge on cation increases, okay, its ionic radius decreases. I have just shared this thing with you. Okay, like aluminium plus 2 plus 3 plus. So 3 plus will be smallest. Why? Because its effective nuclear charge has increased. 3 plus will be what? This smallest because its effective nuclear charge is maximum. Whereas aluminium effective nuclear charge is minimum if I compare aluminium and its iron. Then same thing iron plus 2 plus 3 plus. What happens? The charge keeps on increasing, and since the charge keeps on increasing, its effective nuclear charge keeps on increasing, and since effective nuclear charge increases, its ionic radii decreases. Clear? One more important point over here that I have written for you all. The smallest cation that we have is H plus, and H plus is nothing but equivalent to proton. Okay, it is what? Equivalent to a proton. It is equivalent to a proton. Clear? Sure. Next, what are the factors? Another factors. If the charge on an ion increasing, I have already discussed this thing with you. If the charge on an ion increases, that means its size increases, ionic radii increases. In terms of cation, it decreases. In terms of anion, it increases. That means oxygen, O minus, O2 minus, right? So its size keeps on increasing. N minus, N2 minus, N3 minus, again charge keeps on increasing. Sorry, charge, negative charge, that is anionic charge keeps on increasing, and hence the ionic radii also keeps on increasing. Clear? Now, what if they are isoelectronic species? What is an isoelectronic species? Having the same number of electrons. Okay, so if we'll see this elements from C4 minus to Al3 plus, they have same number of electrons. So in such cases, for isoelectronic species, please remember this equation. Ionic radii is inversely proportional to atomic number. Ionic radii is inversely proportional to what? Atomic number. That means, see, carbon has atomic number 6. Aluminium has atomic number 13. So, ionic, okay, radius is inversely proportional to what? Atomic number. Since atomic number of carbon is less, its ionic radii will be the maximum. See. C4 minus is max, Al3 plus is small. Why I can say that? It's very simple. Say they all consist of 10 electrons, no doubt in that. That means the number of repulsions given by 10 electron will be the same in every cases, but it has 6 proton, 7 proton, charge increases, positive charge increases, that means nuclear charge increases. Nuclear charge increases by unity, by unity, by unity, by unity, by unity, by unity. So that means as compared to C4 minus, that is carbon, and as compared to aluminium, aluminium has more nuclear charge or the maximum nuclear charge in the given example, and that is the reason, since it has a maximum nuclear charge, it has maximum effective nuclear charge, and since it has maximum effective nuclear charge, we can clearly say that its ionic radii will be the smallest, because aluminium ion has maximum nuclear effective nuclear charge, and hence its radius will be the minimum. Got it? Clear? Sure? Oh, I hope that you don't have any doubts, any difficulties till now. Okay, let us discuss one more thing. Okay, after that thing we can just stop for today. Okay, we'll discuss one more thing and we can stop. Okay, and that is the smallest cation. Okay, the smallest cation is F minus ion. It's not H minus ion. It is fluoride ion. Is the smallest, sorry, not smallest cation, what I am saying. Smallest cation is H plus, but I am talking about smallest anion. Okay, we need to discard this thing. We are talking about smallest anion. Okay. Reason why H minus is not the smallest anion? The reason is, first of all, electron repulsion. The moment if you add, hydrogen consists of how many electrons? One electron. If I add one more electron, the number of electron becomes double, and hence the repulsion becomes double. And hence our repulsion directly becomes what? Double, which cannot be experienced in any other atom. Second, effective nuclear charge decreases drastically, because since the repulsion has become double, its effective nuclear charge will decrease what? Drastically. Last, electron to proton ratio is twice, that is 100%. Electron to proton ratio is what? Twice, that is nothing but what? 100%. And that is the reason why, hence H minus ion increases, size increases drastically. Okay, clear? Sure? Got it? Any doubts, any difficulties? No one? No. Let us solve this question. Okay, and then we can stop over here. Which of the following orders of ionic radii is correctly represented? Correctly represented. The question was asked in 2014. Now, H minus, we know that if the atoms are same, okay, if the atoms are same, that means anion will be maximum and cation will be minimum. But here, anion and cation are nearby, so this should not be the answer. Okay, for this, if this want to be the right answer, you have to write it as H minus, H and H plus. What about this thing? If you'll see, sodium has 10 electrons, F minus, that is fluoride, has 10 electrons, and oxide ions has 10 electrons. So they both are same. Hence they are what? Isoelectronic. They are what? Okay, they are known as what? Isoelectronic. And for isoelectronic species, I said that ionic radii is inversely proportional to atomic number. Hence, in this case, O2 minus should be more than F minus should be more than Na plus. This should be the order, whereas the order is reverse, and hence this is not the right answer. Right? Clear? Sure. So, see, F minus, O2 minus, Na plus, again this is not the right answer. The right answer is this one, because its atomic number is 8, this is 9, and this is 11. Right? So this is the right answer over here. This will be the smallest one. So this is not the right answer. And certainly this is not the right answer. The right order over here is, again, they are what? Isoelectronic species. So N3 minus will be maximum. Then Mg2 plus. And then Al3 plus. So none of the answers is matching. Mostly what mistake I might have done is, this order should be like this. Okay, and if we are making this order like this, so we can easily say that, okay, we can easily say that this is the right answer. Clear? Sure? Got it, guys? Okay, so yeah, this can be one of the cases. Okay, but yes, this might be a typographical error. So that is the case. Next, the correct order of the decreasing ionic radii among the following isoelectronic species is, again, came in NEET 2010, right? Careful investigation shows that they are again what? Isoelectronic species. They are again what? Isoelectronic species. And since they are isoelectronic species, we should know that its ionic radii is inversely proportional to what? Z. That is the atomic number. So out of all, sulfur has atomic number how much? Sulfur has 16. This is 17. This is 19, and this is 20. So the order should go in this way. Okay. If you want ionic radii to be maximum, its atomic number should be minimum. So I'll go with this order. S2 minus will be having the maximum size then as compared to Cl minus ion, that is nothing but 16, will be more than 17, which will be more than 19, and which will be more than 20. So K plus and Ca2 plus. So this is the order, right, guys? This is the order, right? So which is the option over here? S2, Cl minus, K plus, Ca2 plus. That means option C is the right answer. Clear? Any doubts, any difficulties, guys, in this particular concept? Guys, any doubts, any difficulties in this particular concept to any one of you? No one? Sure? Perfect. Next, coming upon to ionization enthalpy. The word itself means what? Ionize. That means you have to ionize an atom. And how does ionization happens? When you remove the electron, when you have to remove the electron completely from the atom, right? Clear? So it is the amount of energy supplied or given to an atom so that it can remove, or we can easily remove that valence shell electron. Okay. So it is the minimum amount of energy required to remove a valence shell electron from an isolated gaseous atom from its ground state is known as what? Ionization enthalpy. It can be represented in this way. Okay, and ionization enthalpy is denoted in this way. I am not interested in the definition. I have already read it. You know the concept. Let us proceed further. Now, there is something known as successive ionization enthalpy. This is an isolated gaseous atom which has effective nuclear charge like this. For an example, 1 as a matter of fact. Let us give us some number. So we are trying to remove the electron. So the energy required to remove this one electron from this isolated gaseous atom is IE1, and it gets converted into cation. We know that since a gaseous atom, a neutral atom is getting converted into cation, its Z effective charge will increase. That means it becomes 2. So what about radius? Suppose this is R1, this is R2. Can I say the radius decreases? Now the cation radius will be less than the corresponding atom. Answer is yes. Again, I am removing one electron. That means now the energy that has been required to remove the electron is ionization enthalpy 2. Again, effective nuclear charge increases. That means, can I say that the effective nuclear charge keeps on increasing? Let us give the number as 3, right? And its radius is what? R3. Again, it decreases because they are inversely proportional. We know that effective nuclear charge is inversely proportional to what? Radius. That's what I am doing over here. Okay, and there are 2 to 4 conclusions that we are going to derive from this successive ionization enthalpy. So please make a note of it. Again, if I'll supply some energy to remove one electron, it will be IE3. Effective nuclear charge increases. Let us give the number as 4. So again, effective nuclear charge has increased and its radius has decreased. And if I supply one more, it is I4, increases, and let us give this number as 5. R5 decreases. Okay. Clear? So I hope this much is pretty much clear to every one of you, right? But what is the important point over here? First of all, if you just keep on ionizing an atom, its effective nuclear charge keeps on increasing. Okay, its effective nuclear charge keeps on increasing, but its radius keeps on decreasing. Its radius keeps on decreasing. What about ionization enthalpy? Ionization enthalpy also keeps on increasing. Why? Because effective nuclear charge has increased. And since the effective nuclear charge has increased, so my dear student, what is effective nuclear charge? It is the force that is acting on the valence shell electron. It is a nuclear force that is actually acting on a valence shell electron, and that is increasing. That means what? The force of attraction is increasing, and since that force of attraction is increasing, you require more and more energy to break that force of attraction. That's why ionization enthalpy keeps on increasing. So that is the reason why IE4, the fourth ionization energy over here, is maximum than third, then second, and the first one. And please take a hint over here, guys. If ionization enthalpy changes suddenly, like suppose this is 30, for an example IE1, let us go on the opposite side of it. Okay, suppose this is like 30, 65, 115, 300. Can you see here? Okay, nominal change, something like double. But what about here? It is almost 3 times. The change is almost 3 times. It simply says that till this point, the noble gas configuration was achieved. And since you have supplied ample amount of energy to disturb that noble gas configuration, that's why you are seeing this drastic change in ionization enthalpy. Clear? So whenever you see this drastic change, you must assume that the noble gas configuration has been disturbed. Clear? So this will help you to give the right answer in the examination as well. Clear? Sure? Got it? Now, proceeding further. What are the factors affecting ionization enthalpy? The first, size of an atom or an ion. Okay, so more the size of an atom, less is the ionization enthalpy, and that is inversely proportional. Effective nuclear charge, it is directly proportional. More the effective nuclear charge, more is the ionization enthalpy. Okay, then coming upon to penetrating power, if n, that is nothing but what? The number of shell remains the same. Then we know that penetrating power also plays a very important role. If it is present in s orbital, if the electron that has to be removed from s orbital, we know that on s orbital the nuclear force of attraction is maximum. So it becomes very difficult to remove from s orbital. Then it is a bit easier to remove from p orbital as compared to s orbital. Then d, and then f. Removing electron from f orbital is pretty much easy as compared to any other orbital. Talking about electronic configuration, yes, half filled, completely filled orbitals. Okay, half filled and completely filled orbitals will show reluctance to give away the electron easily because their stability will be disturbed. Okay, half filled orbitals like p3, d5 and f7, and completely filled like p6, d10, f14. Clear? Sure. So please remember this thing. Okay, these are the factors that affect what? Ionization enthalpy. Okay, proceeding further. For same atom is same, the electronic configuration is not considered whether it is half filled or fully filled. Okay, for the same atom, the electronic configuration is not considered whether it is half filled or completely filled, and the order will go in this way. The cation, if the atoms are same, the cation will always have maximum ionization enthalpy as compared to neutral atom, and then as compared to what? Anion. Clear? Trends is pretty much simple. From left to right, we know that in Z effective increases, the size decreases, and hence ionization enthalpy also increases because effective nuclear charge is directly proportional to what? Ionization enthalpy. Effective nuclear charge remains same, but size increases. Size is inversely proportional to ionization enthalpy, and hence ionization enthalpy decreases. So that's why S block element lose electron very easily, and halogens lose electron very difficult way. Okay, clear? Sure. Right? Any doubts, any difficulties to any one of you till now? Any doubts, any difficulties to any one of you? Guys? Any one of you? Any doubts? No one? Perfect. Let's proceed further. Now, let us compare ionization enthalpy. Ionization enthalpy will be the last session for today. Last topic for today as a matter of fact. Now, if I talk about first period, no doubt in that helium will have more ionization enthalpy than hydrogen. Reason? Pretty much simple. Helium has an inert noble gas configuration. Its duplet is completed, whereas electron duplet is not completed. So removing electron from hydrogen becomes easy as compared to helium. Second period is pretty much important, and question is been asked on second and third period. If you can see, I have shown some arrows. that arrow shows something very specific. See, ideally neon, okay, from left to right, ideally the order should be what? From left to right, effective nuclear charge increases and hence ionization enthalpy. So can I say that ideally the order should be neon, then comes fluorine, then comes oxygen, then comes nitrogen, then comes carbon, then comes boron, then comes beryllium, and then comes lithium. This is ideal condition, but this is not observed. Why? The reason comes over here why it has not been observed, and the reason over here is, if you see about nitrogen electronic configuration is 2s2 2p3. This 2p3 has half-filled stability. It has what? Half-filled stability is there, and since it has half-filled stability, half-filled stability, removing electron from nitrogen becomes difficult. Removing electron from nitrogen becomes what? Difficult. But see about oxygen. Oxygen has 4. That means, can I say that if oxygen lose one electron, it will get the stability, it will get half-filled stability of nitrogen, right? अगर ऑक्सीजन यहाँ से एक इलेक्ट्रॉन छोड़ता है, that means क्या होगा? उसको क्या मिल जाएगी? half-filled की stability मिल जाएगी, and since it gets the half-filled stability, oxygen lose electron more easily, and hence its ionization enthalpy decreases. Due to partial or half-filled stability, nitrogen has reluctance to give away the electron. Clear? Sure. So this is the case, and hence nitrogen comes before oxygen. Nitrogen comes before oxygen. Now normally then carbon के बाद क्या आना चाहिए था? बोरॉन. कार्बन के बाद बेसिकली क्या आना चाहिए था? बोरॉन. But what comes is beryllium. Why? See, in boron you have to remove electron from p orbital, whereas in beryllium you have to remove electron from s orbital. We know that removing electron from s orbital is really very difficult as compared to p orbital. That means p orbital से electron निकालना आसान है as compared to what? s orbital. s orbital में difficulty होगी. Second reason, यहाँ पे आप stability disturb कर रहे हो. Paired electron है, that means कोई unpaired electron नहीं है, orbital भी completely filled है, तो यहाँ पे आप क्या disturb कर रहे हो? Stability. Whereas यहाँ पे देखो 2p, p consists of 3 subshells like px, py, pz. That means total 6 electron can be accommodated. मतलब सिर्फ एक ही इलेक्ट्रॉन है, 5 जगह खाली है, राइट? अगर वो एक इलेक्ट्रॉन भी दे देगा तो क्या मिल जाएगा? अगेन s ऑर्बिटल की स्टेबिलिटी मिल जाएगी, and hence boron give electron easily as compared to what? Beryllium, and that is the reason beryllium comes before boron. Clear? Sure. The same concept you can apply in period number 3. Okay, removing electron from s orbital is difficult as compared to p orbital. That's why magnesium comes before aluminium. Magnesium comes before aluminium. Similarly, phosphorus has partial or half-filled stability. That is the reason phosphorus comes before sulfur. Phosphorus comes before sulfur. One important pointer over here: in any period, ionization energy of inert gas is always maximum. No doubt in that. Clear? Sure. Got it, guys? Got it? Perfect. Okay, so yeah, ionization enthalpy, if I talk about top to bottom, obviously it keeps on decreasing because shells add होते जाते हैं. From top to bottom what happens? Shell keeps on adding, that means radius keeps on increasing, right? Effective nuclear charge almost remains same, इसमें से कुछ change नहीं होता, but ionization enthalpy क्या है? It is inversely proportional to radius, and hence ionization enthalpy decreases as radius increases. Similarly, you can see it over here and in here. Okay, clear? Next, boron family. Yes, there is some problem with the boron family, as I have already discussed with you, right? If you'll see the boron family, there are some exceptions. In boron family, boron is maximum, which is expected to be maximum, but normally क्या होना चाहिए था? ये trend follow होना चाहिए था. This has to be the trend, but this is not the right answer. Okay, from boron directly comes is what? Thorium. Why thorium? Because thorium consists of what? F orbital, filling of F orbital. Okay, and d orbital as well. So thorium consists of F, filling of F and d orbital both. And d and F orbital, they both have a very poor shielding effect. Okay, they have a very poor shielding effect, and due to that poor shielding effect, the electron present, okay, due to the poor shielding effect, the electron present in the outermost shell of thorium, that is nothing but p orbital, okay, it experiences an extremely high effective nuclear charge, and due to that very high effective nuclear charge, its ionization enthalpy increases. So after boron, what comes is thorium. Okay, and I've said over reason as well, lanthanoid contraction, that's why thorium. Then comes gallium, due to what? Due to what? DD transition or transition contraction. Okay, DD contraction or transition contraction, and then aluminium, and then helium. Clear? Sure. Got it. So yeah, please try to remember this thing. Over here in carbon family, again lanthanoid contraction creates a problem in last thing. Okay. Ideally क्या होना चाहिए था? Carbon, then silicon, then germanium, then tin, and then lead. But होता क्या? Lead and tin. होता क्या? Lead and tin. Clear? Sure. Got it. Next. Yeah, depending upon the ionization enthalpy. Okay. ये वाला एक काम करते हैं अपन. Since time is up, we'll be discussing this concept later on. Okay. We'll be discussing this concept later on. So yeah, that's it from my side, guys. I hope that you must have understood whatever topic we have discussed till now. Okay, so stay tuned to our channel Infinity Learn by Sri Chaitanya. That is, and this is a new channel, that is Infinity Learn NEET. So do subscribe our channel. Do not forget to like, comment, share, and subscribe this channel. Okay. Till then, guys, let's discuss the next part of it some other day. Till then, take care, guys. God bless you. Keep smiling. We'll meet soon.